previously mentioned, we are going to be looking at derivatives of logarithms today. And just like with sine and cosine and some of our trig derivatives, I like for us to find our derivatives by group in a way. So we are going to actually use what we learned yesterday, which is the derivative of e, to help us use implicit to find the derivative of the natural log. So it says find the derivative of y equals the natural log of x using implicit. So let's say you forgot how to find the derivative of the natural log, but you remembered how to find the derivative of e. We could use the properties we talked about on Friday to e both sides. So that would give you e to the y equals e to the natural log of x. And then after you did that, you know that e and natural log are inverses of each other. So what we could do at that point is cancel the e and the ln, and you get e to the y equals x. Now yesterday we learned how to take the derivative of e to the y. So the derivative of e to the y becomes e to the y, and then the derivative of y is dy dx. So e to the y dy dx equals the derivative of x, which is 1, solving for dy dx, we get dy dx equals 1 over e to the y. But we started our function with y equals. So what we can do is replace y and e to the y with substitution, because y is really the natural log of x. So we want to give our answer in terms of x instead of y. So it becomes 1 over e, substituting natural log of x in for y. We get 1 over e to the ln of x. But what does e to the ln of x become? Well, e and ln are inverses, so it becomes 1 over x. So, moral of the story, the derivative of the natural log of x is 1 over x. The derivative of the natural log of x is 1 over x. So, just like yesterday, the likelihood that we simply derive the natural log of x is slim to none. More than likely, what we will derive is the derivative of the natural log of a function. So, it's important to take into account the fact that the derivative of a natural log of a function, u, is 1 over u, and then once again times du dx. So just like e to the x or e to the u becomes e to the u times du dx, the natural log of u becomes 1 over u times du dx. So, if you're asked to find the derivative of the natural log of x cubed plus 1, what we want to do is determine what is my u, what is my du dx, so my u is what's inside the natural log, so it's x cubed plus 1. Du dx is the derivative, which is 3x squared. Derivative of 1 is 0. So, dy dx, which is the derivative of y with respect to x, is 1 over u times du dx, or simply 3x squared over x cubed plus 1. Again, kind of like what we talked about yesterday, you cannot simplify the x squared and the x cubed because there's subdivision in my denominator. So that denominator is kind of like in jail, meaning you cannot simplify it with its numerator. Number 2, we have y equals the natural log of sine x. So my u value is the inside, which is sine x. My u prime, or du dx, remember they're the same, is the derivative of sine. Well, the derivative of sine is cosine x. So my y prime is 1 over sine x times cosine x. But cosine x over sine x is cotan. So the derivative of the natural log of sine x is cotangent x. You can also have a natural log inside a function. So this is a function composed in a function composed with a function. So really I have 3 functions right now. I have the square root, the natural log, and 2x. So dy dx is the derivative of the outermost function first. So that's the square root. So we're going to start by taking the derivative of the square root. So that's 1/2 ln 2x to the negative 1/2. And then the chain rule says we have to multiply by the inside of the square root. So now we're going to do the derivative of the natural log of 2x, which is my formula of 1 over the inside, which is 2x, times the derivative, which is 2. And now we're just going to clean this up. So 1/2 and 2 cancel. Negatives are a no-no in our exponent. So we get 1 over 2x. And you could rewrite it as a square root ln 2x. Or you could write it as the power of ln 2x to the 1/2. In example 4, we have the natural log of this very, very complicated quotient. So way back on Friday, I taught you that natural logs can be expanded or simplified. So could we take the derivative of this natural log exactly as it is now? Yes. You could find your u. You could find your u prime using the quotient rule. And this would go on and on and on, etc., etc. So could I do it this way? Yeah. However, if you recall Friday's lesson and the fact that we can take a single, it's okay if you wrote it, just right underneath it, there's still plenty of space. The fact that we could take a natural log from a single form to expanded form. So what I mean by that is if you have a natural log containing division, that's the same as the natural log of the numerator minus the natural log of the denominator. Right? We're all in agreement to this. And the square root of x minus 2 is really the same as saying the function to the 1/2 power. But we know that if we have a natural log raised to a power, we could bring that power out in front as a coefficient. So that complicated quotient rule can become a much simpler set of two natural logs So now I could take the derivative of that simplified form. So it's the natural log's derivative of the first term, which is 1 over u, which is x plus 1, times the derivative of x plus 1, which is simply 1, minus 1/2 times 1 over u, which is x minus 2, times the derivative of x minus 2, but the derivative of x is 1, and the derivative of negative 2 is 0. So my derivative becomes 1 over x plus 2 minus 1 over, x plus 1 minus 1 over 2 x minus 2. I don't have any square roots. I don't have negative exponents. I didn't have to do the quotient rule. So do you see how understanding and knowing how to take a logarithm via Friday's lesson and the quick review I made you do yesterday is such an important skill set for finding the derivatives of these complicated functions? Thank you all for answering yes. Okay. So we have other natural logs that we have learned about as well. So what I want to do, and I'm going to put that back up, don't worry. I just want to start with this natural log. So we have the derivative of the log of a to the u. And if you recall, we had a formula called the change of base, which said that the log of a to the u is the same as the natural log of u over the natural log of a. So that's called the change of base formula. So the change of base formula said that the natural log of a to the u is really the same as the natural log of u over the natural log of a. And back in the day, our calculators used to not be able to take a log to a base of a other than 10. So you had to use this change of base formula. But now our calculators are so smart and they have this added feature where you can take the log of any base. But going back to what we just discovered, we can actually prove why the derivative of the log base a of u is equal to what it's equal to. So we're going to prove why the derivative of that log is actually equal to what it's equal to using change of base. So let's derive the natural log of u over the natural log of a. So I need the quotient rule because I have division, as well as my new natural log rule. So the quotient rule says denominator times derivative of the numerator minus the numerator times derivative of the denominator. The natural log of a is a constant, so its derivative is 0. The natural log of a is a constant, so its derivative is 0. All over the natural log of a squared. So you get ln a times 1 over u times u prime over ln a squared. But we got an ln a up top and an ln a squared on bottom, so we can cancel 1 away. And we get 1 over ln a times 1 over u times u prime. So we actually talked about it a little bit with the integration example, and we've talked about it with limits. You can actually bring out a constant when you find its derivative. So if I asked you to find the derivative of 3x, that's kind of like saying 3 and then the derivative of x, right? Because the 3 is just tagging along. And that became 3 because the derivative of x was 1. Well, the same could be true here with this example. I could actually have said, okay, that ln of a is a constant. So this is really like finding d dx of ln u. And you would see once again that you got 1 ln A times 1 over u times u prime, because the derivative of the natural log of u is 1 over u times u prime, times that constant 1 over ln A. Good? So, if you have y equals the log of 10 of 2 plus sine x, we're just going to apply our rule. So the 10 is like my a. This 2 plus sine x is my u. So my derivative is 1 over the natural log of a, which is 10, times 1 over the u value, which is 2 plus sine x, times the derivative of my u value. Well, the derivative of 2 is 0, and the derivative of sine is cosine. So cleaning that up, you get cosine x. And here's where you got to be careful. It's natural log 10. But you got to make sure you put 2 plus sine x in parentheses. Or you have to distribute the 10 with the natural log to both. But if you did not put parentheses around the 2 plus sine x, it would be incorrect. So you can't put your parentheses around the natural log 10. They have to be around the 2 plus sine x. So that you get this idea that that natural log of 10 distributes to both. Yes?
So if we just distributed it instead of putting in parentheses, would that be wrong?
No. Like how I wrote the second answer, if you had that, that's fine. But what I was noticing, and we're going to talk about it when I get back to your test, is some of us were not writing parentheses. I hope this erase is okay. Like here, you were trying to just put them around this. But that's not, they're not the same thing. So I'm starting to get picky about making sure algebraically we're doing things correctly. Same with, you can't put a dot between the two of them, because once again, that's only signifying to me that the natural log of 10 and the 2 are being multiplied to each other, not that that natural log of 10 is also going to the sine. Does that make sense to everybody for what I'm trying to explain? The final formula we're going to learn, and yes, you have to memorize every formula we've learned this week, guys, is the derivative of a to the u. A represents a constant. It's kind of like my e, right? A is kind of like e. E is just special. So a is like e. E is a constant. So if you think back to the derivative of e to the x, or e to the u, we said the derivative of e to the u was equal to e to the u times u prime. But what we'll notice is different is this one has the natural log of a in it. Ironically, our e technically has that natural log in it for its derivative. It's just that, what do we know about the natural log of e? Natural log of e is always 1. So technically, when I taught you the derivative of e to the u yesterday, that ln a we're seeing here was really in our derivative. It's just that the ln e becomes 1, so we don't make the students memorize it that way. but technically it's there. Because E and A both just represent numbers. So you have y equals 10 to the 2x. So 10, just like the other e to the x problems, we rewrite 10 to the 2x. The derivative of a to the u is always a to the u. Times ln a, where a in this case is 10, times u prime, which is the derivative of 2x, so 2. These don't really simplify. Do not multiply 2 and 10. Everybody wants to make it 20. Order of operations say you have to do 10 to the 2x before you can multiply the 10 and the 2. Don't multiply them. The only thing you could really do if it bothered you is rewrite that as 2 ln 10 times 10 to the 2x. Good? Okay, so your homework tonight is a continuation of the homework from yesterday in our textbook. We are moving over to 11 to 16 and 17 to 27 odd. So that's why I told you didn't have to turn in the 1 to 10 yesterday, because eventually we're going to go over all of the homework from page 178 at once. And speaking of going over homework, since we did the 3.9 quick review out of order, if you'd like to see the answers to the 3.9 quick review are up on the board as well. So I've checked those homeworks. I'm putting in those scores, but here are the answers if you'd like to see them. Because I had removed them from yesterday's lesson video, just so it wasn't confusing. Okay, so at this time, if you want to take a quick restroom break, get up, move around, stretch out. When you come back in, we will go over your Chapter 3 tests, and then you can have the remainder of class time to do your homework. But I think going over the tests, there's some stuff I want to talk about.